So now I'm going to give you a new definition of supremum, and some of you have already thought about this a little bit, just didn't realize you were thinking about it. So this is a second definition, or you can actually prove this definition by using the other definition, which some books do. We're just going to use it as definition number 2. So if I have a non-empty set of real numbers that's bounded above, and I actually should say that, not imply that, then the soup is the soup if for every epsilon greater than 0, there exists an element x belonging to A such that if I subtract that little off of x, it dips down below x. So it's kind of like that upper bound thing that I did in the other proof. It dipped into the set. So if you look at the picture, think of A as being an interval. Here's S, the soup. Epsilon is given to you. S minus epsilon dips into the set. So no matter what epsilon they give you, S is such a tight bound that subtracting off just a little hair dips you into the set. And there's the x that's between S minus epsilon and S and A. So in class, we're going to go through, just get familiar with this idea of an epsilon because it's weird when you first see it. But I'm going to do a proof using that epsilon definition. And your proof on the homework is very similar. So in this proof, the first thing you're going to have to do is get a decent numerical guess as to what the soup of A is, kind of like that worksheet we gave you the other day. So if I plot this, you see it's an increasing set of points that's bounded above by 1. So my guess is that the soup of A is equal to 1. Break this down as an if-then statement. If S is the soup, then S is 1. Use the proof guide. We know S is the soup. That means with the epsilon definition of soup, that for every epsilon greater than 0, I have an element x belonging to A such that x is, so I just rewrote the definition down. I'm supposed to show S is equal to 1. So I'm supposed to show, and I wrote it down. And sometimes people ask me, why do you have to write everything down? Well, the reason I wrote it down is now I see this, I have an inequality. I'm supposed to arrive at this inequality over here, right here. So I have to produce an x. I have to show there exists an x. So I have to actually construct it and show you what that x is, such that x is bigger than 1 minus epsilon. So how do these proofs actually work? I'm actually supposed to show this inequality over here. I always start here. If they say for every epsilon greater than 0, so I'm going to pretend that there's a guy with a bag of epsilons and he pulls an epsilon and hands it to me. So every one of these epsilons he's going to pull from the bag, I should be able to rework my proof. So the guy pulled the epsilon from the bag, gave it to me. So I say, let epsilon greater than 0 be arbitrarily given. So they just gave me one. My proof should construct an x so that x is bigger than 1 minus epsilon. I need to find that guy. Anytime you have a there exists proof, you have to somehow show that exists. Some proofs are slick and they don't actually come up with that x, but for the baby real analysis, a lot of times you have to have a candidate for what that x is. So remember, we start there. There's my set. I'm going to look at my set all written out. So I didn't write out the tail end here, the other bracket, but this is what it looks like. And I'm going to write down my end here part. This is where I'm supposed to end. Well, look at this. Those epsilons sure look like 1 over 3 squared. I'm subtracting 1 over 3, 1 over 3 squared, 1 over 3 cubed. And here I'm subtracting epsilon. My x's all look like this, 1 minus 1 over 3 to the y. If I took an arbitrary x, that's what it would look like in that set. So this is my scratch work. So I really need to find that y that makes this happen. So in a lot of the analysis proofs, the trick is to write down what you have to show with everything replaced and then work backwards. Okay. Unravel this inequality. If I get rid of the 1s and I multiply both sides by minus 1, I really want to say they gave me an epsilon. can I find a y so that 1 over 3 to the y is smaller than epsilon? Well, I can, because 1 over 3 to the y gets close to 0 as y gets larger and larger and larger. So I certainly can find a y large enough, no matter what, like they gave me 0.001, I can still find a y large enough so that 1 over 3 to the y is smaller than 0.001. So I just want to warn you, some profs will want you to prove that, not just say that. And if you do that, it's a proof by contradiction. My advice to you is, if you find out that a prof wants you to prove to that detail, then what I would recommend is putting that as a lemma and separating that out of your proof. Say, oh, refer to lemma 1 in my appendix, because it's really confusing to see a proof within another proof. So here's what the clean proof looks like. So I want you to see it all done. Now that I've unraveled everything, figured everything out, I do have to write a clean proof. And this is what real analysis, baby real analysis teachers like to see. So you start out with let epsilon greater than 0 be given. Then there exists, that symbol means there exists a y, so that epsilon is bigger than 1 over 3 to the y. If they give me a huge epsilon, I can get a y large enough so epsilon is bigger than 1 over 3 to the y. If they gave me a small epsilon, I can find such a y. By multiplying both sides by -1, I get this inequality over here. Notice I give the direction of what I'm doing and make it very clear. Adding 1 to both sides yields that inequality. Do not leave these things out. You're making it so easy for your reader. That's the idea. You're arguing with your reader, and you're trying to convince your reader of something. Leaving out details convinces nobody. Using words like clearly and obviously are just ways to hide the truth. So the truth is proof, and you have to put everything down and put all the details down. Now, by the structure of my sequence, x equals 1 minus 1 over 3 to the y is an element of A. So if by the epsilon definition of sup of A equals 1, because given epsilon greater than 0, I found an x in A so that 1 minus epsilon is greater than x, or less than x. Moreover, 1 is already an upper bound. I didn't even show that, but it's an upper bound because if I subtract any positive number off of 1, 1 is bigger than 1 minus 1 over 3 to the n for all n. So that completes the entire proof. So that was tricky. Pause it, rewatch it. I know I'm going to give you a worksheet to actually go through this proof. So you'll have to watch this. I'm going to present it in class, so get a chance to see it and get familiar.